Question. What does area have to do with integrals? What does area have to do with integrals? I want one person per group, hopefully at least one of you, to grab out a calculator. Is there at least one calculator per group? If not, there's two. Go ahead and pass one around to another group without one. I know Thomas has his, as always. I want you guys to try to get this area with this answer somehow using your calculator. And I gave you a hint yesterday that you can use the integral feature. You can go under the y equals if you want. There's a way to do it on the graph itself. There's a way to do it from your home screen using. Real quick, groups, turn together. Everybody looking at the calculator. See if you can collaborate. How to get 7/3 and double check my work. Oh no. Oh, nobody? Does any group have an extra calculator? Here, you guys use mine. From the home screen, use the math button. Or from the graph, use the second trace button. If you get one, try to go figure out how to use the other. Can you get 7/3 on your calculator? What happened? You okay?
Yeah, I just.
Okay. Okay. Oh. Good. Good. All right, if you already did it in the home screen, try to go do it in the graph. I have this group up here doing it in the graph. Home screen, you hit the math button. On the graph, you go to second trace. But you have to graph the function first, the integrand first. The graphy one is kind of cool because you actually see it shade. Not throw shade, but put shade where it needs to be. You can type in numbers too. If it's asking a question, you can just put a number, type a number. See it? And it shades it? Isn't that cool? Did you get the shading working? Function. And then second trace, there's an option for an integral. Don't worry, when it asks a question like lower limit, you can always just type in a number and then hit enter. And then type in 0 to 1, right? Because 0 is the bottom, 1's the top.
Why are they all the same?
Oh, you have to do it again. You lost. Do you guys get the graph? You see how it shaded it? Wait a minute. Oh, and that's why? It asks you for lower and upper. You can actually just type it. 0 to 1. Yeah. What are you graphing right now? Oh, no. Just graph the integrand. Okay, so those of you guys that got a group that got the home screen to work, I want you to walk me through step by step, because I still haven't figured out our licensing with my poor little SmartView calculator up here, so it won't open. Thomas, how'd you get the integral to work from the home screen?
I hit math.
Good.
And I went down to 9.
Good.
Function, INT.
Good.
And then put in all the numbers.
Function int, function integrate. Does that make sense? Cool, keep going.
We put the 0 and the 1 in the integral.
Good.
And we put in the function.
Good. Good. If you guys want, you don't have to do it right now, but you could have also used whether it's a t, whether it's a y, whether it's a p. You could have put in like a t squared plus 2 dt. You could have done a y squared plus 2 dy. If the integral is in terms of another variable, it has absolutely no, for our purposes, has absolutely no bearing on the answer. But the reason why I have that available is because if you were to ever change this variable, you'd have to also change that variable, but otherwise you can just put dx. Good. And did you get 2.333333? Perfect. Someone else who got the graph to work. Different who got the graph to work. How'd you do it? Michael.
Okay, so you have to first graph the function, and then once you do that, you go to second trace, then you go to the integral sign,
Mhm. Good.
and then you type in the lower and the upper limit.
Good. I saw a lot of groups using the cursor button trying to do it, but did you hear what Michael said? Just type it in. Type in 0, type in 1, enter. And then what happened when you put in 0 and 1?
Just shade in the little thing.
Cool. It shaded it and you got 2.33333. Perfect. Did you guys get it to work? Okay. Why is that kind of cool? Remember how there's a graphing calculator portion to the exam? There are a few of them, not every single one, but a few of them where they realize the by hand work is way too hard or way beyond what they would expect you to be able to do in an AP exam they've given you. So if ever you are in a graphing calculator portion and there's an integral to solve, guess how you're supposed to solve it? A definite integral to solve. Wait, what's the difference between indefinite and definite? Indefinite plus c, you're anti-deriving. Definite has bounds. How are you going to solve any definite on a calculator portion? Calculator. Now, what would my advice be? Home screen. Can anybody tell why? Why would my advice be the home screen math option if you're just solving it? It's faster, less time, and you don't have to worry about the zoom. Because maybe you're going from like 13 to 155. Your graphing calculator is not going to like that if you're in a 10 by 10 window. Does that make sense? Okay. So my advice would be like for a word problem or for anything like that, if you're plugging into a formula, we're going to see some with total distance traveled and displacement and different things like that. Average value, which is different than average rate but similar. You need to know the formula, but it uses an integral and you could use your calculator to solve. And that's why on free response questions, on the calculator portion, if they ask you to find a certain quantity that needs an integral, they will never, ever give points for work. So you waste your time if you try to do it by hand. Anyway, can your calculator solve indefinite integrals? No. But can it solve definite integrals? Yes. Okay. So then, moving on. I just wanted you guys to be able to see that. That's not actually going to help you tons and tons for this section because if you guys remember the title, my screen is totally, yep. Okay, hi. What's the title of this section? Okay, area. But then over here, on this page, what's the main heading? Approximating. Stink-a-dink-a-dink-a-dink-a-dink. Now, if we approximate, and we approximate somewhat close, should it be at least close to what your calculator would say is the exact area? Yes. But the problem is in the AP question, if it asks you to approximate a certain way, they might put the exact area as one of the answer choices, and it will be wrong because it's not the approximate they're asking for. So be careful. How do we approximate? We can't just use our calculator. We can't just go to this because remember, our calculator programming is using approximation methods. Actually kind of beyond the scope of this class. It's not using quite the basic ones that we're talking about here, but it's using approximation techniques. Because your calculator is like, give me anything and I'll integrate it. The only way it can do that is by using approximation techniques because that calculator can't hold in that huge book of integration tables and go looking and trying to match a given function to each of those formulas and then apply it because it's not you. It's not a person. It can't just randomly do all this problem solving. It needs to have some sort of systematic approach, and that's what approximation methods are. And as we talked about yesterday, if we split this up into, what did we say? Into 3, into 6s, into 9s, into, yeah, if we keep on splitting them up, is it going to get closer and closer and closer? Yes. And if we can put it, and if we can condense it into some sort of sigma notation that our calculator already knows how to do, because some of you guys realize the newer calculators are so fuzzy. We realized last year they know how to do sigmas, right? From 1 to 10, 1 to 100, 1 to 1,000. It might take it a little bit of time. But if we can condense all of these definitions of all these different rectangles, our calculator can deal with it. And it can deal with anything, which is way beyond our abilities. Because with our abilities, we can only deal with the ones that are possible to solve, that fall within the realm of the formulas that we've learned. So anyway, just a little bit of context as to why these approximation techniques are important, not only for programming, but also for dealing with integrands that are more complicated than we know and even maybe impossible to solve by hand. So yesterday we talked about how rectangles, what's the area of a rectangle? Super basic geometry. Base times height. Base times height. And the bases are always going to fall along the x-axis. And so it's not going to be the entire a to b, b minus a. It's not going to be that entire distance because we're splitting it up. And so if we're splitting up, it's going to be b minus a cut into tenths or cut into hundredths or cut into fifths. So that distance cut in two, that's going to be the base. And we're going to make, unlike my picture yesterday, our rectangles equally spaced all the way throughout so that every single base, for this example, I decided to cut it into n equals 10 rectangles. If you guys didn't get that down yesterday, I decided to cut it into 10 rectangles. And so I said, okay, if I'm cutting into 10 rectangles, every single rectangle, remember the sum adds together, the summation adds together all these areas. I said, whatever my a is, whatever my b is, whatever integral you want me to find, whatever that distance is, I'm cutting it into tenths to get 10 rectangles in. I think that's going to be a kind of good approximation. But I don't just need bases, I also need heights. How high do these rectangles go? In some way, shape, or form, they have to be bounded by the curve. And who's the curve? F of x. So I'm going to somehow need my f of x values. But I don't just need one f of x value. I need a second one, and a third one, and a fourth one. And they need to change in order to actually make this good. So to make it change, I need somehow, when the k gets plugged in, I need it to go ahead and move through each of the different jumps. And to make it move through, I'm like, okay, I need it to be 1 of the tenths, now 2 of the tenths, now 3 of the tenths, now 4 of the tenths. And that's going to be great, except here's a dilemma. Right now, if I was to go ahead and plug in 1, I would have a distance of the tenth, but here's something that you might not realize. The way I wrote it yesterday, I do have heights and I do have bases. I actually have the wrong heights. And here's the reason why. If I say I need one of these jumps, here's the sad thing. One of these jumps is actually being measured from 0. Because I'm like, yay, 1 jump. Yay, 2 jumps. Yay, 3 jumps. But I don't need to start from 0. I need to start from A to go 1 jump. And then to go 2 jumps and to go 3 jumps. So the one piece we need to add into our formula from yesterday. Oh, I didn't turn my sound off. Sorry, it was a rough morning. The one thing I need to add into, probably need a sub today. The one thing I need to add into my f of for my heights of each of my rectangles, I need to start at A plus. There we go. Now I'm going to start at A and go 1 jump to go up to my function, then 2 jumps to go up to my function, and 3 jumps to go up to my function. Now this is a cool way of summarizing. My phone's going to go off again. Let me go turn it off. This is a cool way of summarizing, especially if you have like a calculator to do this work. However, a dilemma is that you're not always going to have a calculator to do this. Actually, whenever they ask you to do this, you almost always have to be doing it by hand. So to that end, even though it's really good to be able to see like, hey, we're condensing all of this work into something where we could go and say, hey, we're cutting it into tenths, we're cutting it into hundredths, we're cutting it into thousandths. And with a calculator or with some sort of computing machine, it'd be a lot easier because all of this work would be condensed. We have to talk about how to do it by hand. But we're not going to be almost ever cutting it into tenths or hundreds or thousands by hand. That's silly. We have technology. We have these machines that we can make them do these repeated tasks. And they can do them much quicker and more efficiently than us. But we just want to get the basic idea down. And for the AP specifically, in case you're like, they're just trying to make me do busy work. They're going to kind of force the issue to make sure that you totally... Oh, I forgot that is set up like that. They're going to kind of force the issue and make it so that you have to think a little bit deeper about this whole idea, because they're going to actually, to be honest, whenever they ask you to do this, rarely are the subintervals going to be equally spaced. We're going to start there because it makes everything easier. But when they give you information, almost always it's going to be unequally spaced. I guess that's a word. Unequally yoked is a word, so unequally spaced. Anyway, it's going to be unequally spaced to make you kind of work this out. But when you do it by hand, there is a choice to make. There is a choice to make. You can actually approximate coming from the left. It's called a left-hand sum or a left Riemann sum or a left-hand approximation. Come from the right, and we can use all those same wordings, or come from the middle, midpoints. And we're not specifically talking about from the very left of a whole interval or the very right of a whole interval, but we're talking about each of the subintervals. So one that you guys see down here, I could totally, and let me go ahead and minimize just so that I can draw this a little bit better. I can go ahead and say, like, that be what they're referring to, say, compute the following. Sorry, it's not actually there. If they want us to compute the Riemann sum approximations or the left, right, or midpoint approximations, this right here, what's shaded, is what we would technically say is the integral from 0 to 3 of 9 minus x squared dx, right? From 0 to 3, underneath, between the horizontal axis and the function. That's the exact, but they're not asking us for that. They're asking us to approximate, and we're going to do this 3 different ways. I have 3 different screens, and they're all going to look the exact same way. But the first one I'm going to do the left, the second one I'm going to do from the right, and the third one I'm going to do from the middle. So how do we come from the left? First of all, I need to realize that I'm splitting this into 3 subintervals. Now that shouldn't really seem to be a huge, huge, huge deal. I'm going to come back and fill this in a second. A huge, huge, huge deal. Because in this one, from 0 to 3, well, guys, if I cut into thirds, what? You can write it off to the side, but my delta x is going to be so easy because, well, if I'm cutting a distance of 3 into thirds, I'm just moving by 1, so that's easy. But sometimes you're moving by 1/3, or sometimes you're moving by 2/3 or 4/5. That gets a little bit messier. But for right now, I'm just moving by 1s. Which means if I was to think of this like on a number line, I'm like, okay, I need to go from 0 to, I'm going to go by 1. So I have 1, and I have 2, and I have 3. Here's why I have this little number line up here. If I'm doing, for instance, the first area, I'm going to go ahead and use f of x sub 1 times delta x for a left-hand approximation. Now, you're going to keep going and do more areas, but when you see the very first subinterval, and so in this example, if I'm looking at this entire number line, not just one subinterval, but all the different subintervals, I need to go work through this jump and this jump and this jump. I'm going to start at f of 0 times my delta x, which is 1, and that's going to be my a1. What that looks like on my picture, I'm going to go ahead and at 0 go up to the function, and then I'm going to go ahead and make my first rectangle with that height. So my first rectangle is hitting the function on the left. That's where that left-hand approximation, that wording comes from. So I use 0 as my first value to go ahead and plug in. What's my next value going to be in for my next rectangle? Well, I'm going to it is a sub 2. I'm going to my second rectangle, but my second rectangle is going to go up and hit the function where? It's in between 1 and 2. I'm always choosing the left. So for the first subinterval, I chose 0. For the second subinterval, I'm choosing 1. Yeah. So if it helps, maybe for some of you guys, it might be nice to go ahead and actually For your first subinterval, go ahead and choose 0. For your second subinterval, go ahead and choose 1. For your third subinterval, go ahead and choose 2. Whenever you're doing the left and you work through each of your subintervals, you're always choosing the function value on the left. So you're going to go ahead and for the second rectangle, you're choosing 1 as your height. For your third rectangle, you're choosing 2 as your height. On the picture, that should make sense. Because then for the second subinterval, I'm going to go on the left of that subinterval, go up and hit my function. Then for the third subinterval, I'm going to go ahead and go up and hit that function. That's close enough. And you guys see how these rectangles are coming from the left? They're hitting the function on the left. And since they're rectangles, they're going to jut out. I knew that. Rectangles are going to have some error, we would say. We're going to call this an over-approximation because my actual area is below. It has to do with the concavity of my function because it's concave down. But my left-hand approximation on the left of the rectangles, I go ahead and add those all up. But to add those all up, what do I need to do? I can say my approximate area from the left, or the left-hand Riemann sum is going to equal. And this is where if you are allowed to use a calculator, you can save some time. Because we could go ahead and say, wait a minute, it's just going to be f of 0 times 1 plus f of 1 times 1 plus f of 2 times 1. So even though I like delineating each of them and being like, hey, the first rectangle, second rectangle, third rectangle, ultimately you can write it a whole lot faster. And if you notice a pattern, you can actually kind of have a little more fun with it because what's all the bases? Just 1. And so even if the bases were 2 or 3, they're all equally spaced. I can technically pull the bases out and just say, hey, what's f of 0? F of 1, f of 2. Now hold on, wait a minute. Where are we plugging in those 0, 1s, and 2s? So how could you, if you were doing this in your homework, how could you make this even faster using your calculator? Let's strategize real quick. Is there a way to put a function in one nice little place and then use it over and over and over again like we're doing here? Yeah. Well, you could table, but where do you put the function for a table? Yeah, so I would put the function into y equals. And then, aren't there these cool things called y bars? Do you remember those? People with the calculator, grab it out again. Just because this could save you some time in homework. Ultimately, by hand, it wouldn't be that big a deal to go ahead and just be like, hey, what's 9 minus 0 squared plus what's 9 minus 1 squared plus what's 9 minus 2 squared. Like, that shouldn't be too big a deal for us to actually do by hand. But what if they were to say, hey, now let's make 10 subintervals? Aw, stink. 10 subintervals, first of all, we'd be going by 3/10. So 0.3, 0.6, 0.9, there'd be all kinds of stuff we're adding. So let's strategize real quick. I want you to throw 9 minus x equals. Throw in 9 minus x squared into your y equals. I want you to go back to your home screen. Hit alpha y equals. And then hit those little buttons at the top until you get to y1, y2, y3. Is that the fourth one? Is that trace? And then whatever y you put in, I want you to go ahead and do y1 of parentheses 0 plus y1 of parentheses 1 plus y1 of parentheses 2. You're adding them all together. You're literally just writing this out. And it makes it so much faster, and you avoid some error if you're allowed to use your calculator. I'm going to go by hand. I see 9 plus 8 plus 9, which should end up being 17, and 5 is 22. But do you guys see how to use your calculator? Make sure really quickly, check in with your group and make sure they know what you did, how you did it, because it will save time. What you did, how you did it. If you guys check it, you can go straight, do you guys realize it? Alpha trace. You don't have to go alpha y equals and then over. You can go straight alpha trace to get your y1, y2, y3s. Does anybody in here have a calculator with a yellow button, one of those old school ones? Okay. We are going to have another chance to practice this, and when we do, someone new in the group has to use the calculator. Cool? Okay. So go ahead and give the calculator to someone new. But let's go ahead and get it set up to come from the right. Someone new will be able to test my right-hand one and make sure I'm okay. I'm right. I'm correct from the right. We're still cutting into 3 subintervals. Okay? So still n equals 3. What's my delta x still going to be, guys? Yeah, we're still going by ones. We're still trying to approximate this area that we could find exactly with an integral. But this time we're coming from the right. As we come from the right, we're still needing to do 3 different rectangles. And we still need bases and heights. What are going to be all of my bases for every single one of these rectangles? Because when I come down here, I'm going to go ahead and for each of them, since I need to fit in 3, I'm going to be able to fit in, if I just go by ones, I'm going to be able to fit in 3 rectangles, 1 and 2 and 3, right? So I'm still going to have each of my bases be 1. I know when we do rectangles, we actually do heights times bases, not bases times heights, but either way. And then we know we're needing to go to our function. Have you guys kind of gotten the pattern yet? If not, here's the pattern. We need a height, we need a function value to form our rectangles, and then the bases are going to be whatever our delta x is. If they're equally spaced, it's all the same number. If it's unequally spaced, well, these bases could change if you have wider rectangles and thinner rectangles. Once they force our hand to be unequally spaced, we'll keep it equal, going by ones. Okay, now if we're coming from the left, and we have a given subinterval, we would choose the left-hand one every single time. But if we're coming from the right, we're choosing the right-hand subinterval. So if we're moving from 0 to 3 by ones, if we're coming from the right, it's going to be backwards. For the first subinterval, we're actually going to use 1. For the second subinterval, we're going to use 2. And for the third subinterval, we're going to use 3. So literally, we can just say, hey, f of 1, f of 2, f of 3. People with the calculators, see if you can start plugging in. I'm going to go ahead and try to do it by hand. So we're finding the approximate area from the right. Ultimately, we can pull out that common base of 1. We are going to have inside f of 1 plus f of 2 plus f of 3. Feel free to reach out to whoever did it the first time if you get stuck. I'm plugging in by hand because it's not too hard. 9 minus 1 squared. 9 minus 2 squared. 9 minus 3 squared, which ends up being 8 plus 5 plus 0. That's weird. This one would hit at 8 at the right. This one would hit at 5 from the right. Oh, yeah, if it hits at 0, there isn't one. Because we're dependent on the curve. That one has no area because it hits on the right, which is on the axis, so he's a 0. Did you guys end up with 13? We give just a couple seconds to make sure everybody in your group is okay. Check in on them. Those of you that did it last time and got it to work, make sure they got it. And we have one more example to be able to hand it off one more time. Yeah. Okay, so you have your y equals, right? Good. So then we're going to have technically our base, but it's just a 1, times, and then you're going to do your alpha trace. Y1 is where your function is chilling, and the parenthesis tells it like our f of. So then you're going to type 1 for f of 1, and that parenthesis for the function notation, and then plus. Now, how did I get to the y's? Do it again. No. Keep it y1. Because we're using the same function over and over. But your parenthesis is going to be 2. And then we have another one, right? F of 3. Tom, that makes sense? Guys, why am I going to call this an under approximation? Yeah, partially the last part of the curve's not even there, and then even if it was there, even if there was a rectangle, what's true about each of these? Because of the concave down nature, when you hit on the right, aren't you automatically always going to be under? Yeah? Although, what if I was doing right-hand approximation? I'd be over. So wait, is it the concavity? Maybe it's not the concavity. Maybe it's the decreasing nature. Because what's happening over here, my function is increasing. So increasing means whatever's on the right is going to be above whatever was on the left. So my rectangle is going to be over. Decreasing means if the function or where the function's decreasing, wherever's on the right is lower than what was whatever on the left. Oh, so lower and upper approximations depend on increasing and decreasing. Okay, so my right one was an under just because this function is decreasing. My left one was an over approximation of 22. What does that mean about my actual area right now? Somewhere between 22 and 13. Well, that seems kind of dumb. Let's try midpoint. Nick, what's up, bud?
If you did half of it with an overestimation and half with an underestimation,
Theoretically,
overestimation like compensate for the underestimation.
yes. Possibly not perfectly depending on your intervals, but fairly closely, yeah. Has to do somewhat with the concavity because this one, the under approximate, has a concave out, like a bulge out sort of to it. Whereas over here, the over approximation has, with that concave down, has a bulge into it. So this one has a little bit extra and this one has a little bit less. Does that make sense? So because of that, it's not going to be perfect, but it is going to be close. Yeah. Approximate area, let's do midpoint. This one gets to be a little bit funny. Not impossible, just a little bit funny. Let's go ahead and talk about, before we even get down to the midpoint, actually doing it. Let's talk about an interval again. Whenever we have a little subinterval, a little piece inside the larger picture of A to B, midpoint's a little rough because we're not allowed to use the left or the right. We have to use the midpoint. How do we get to the midpoint? Well, sometimes it's easy and sometimes we have to figure it out by ourselves. We have to use the middle. Ooh, is there a midpoint formula from way back when? You average the two together? But maybe it's not that hard when we actually get down here. Once again, we are going from 0 to 3. Once again, n does equal 3. So once again, we are going by ones. But the problem is, for each of my subintervals, for a midpoint, we're not using 0 or 1. We're using 0.5. We're not using 1 or 2. We're using 1.5. We're not using 2 or 3. We're using 2.5. So then when I go ahead and set up my A1, my A2, my A3, hopefully you guys have kind of gotten into the rhythm of F of being my heights. Bases are 1 in this case just because that's what happens to be the distance in between everybody. But now I'm plugging in my midpoints. So third person on your calculator, when you're ready, we're approximating area. It's going to be a little harder for me to do by hand. With midpoints. Shouldn't be that much harder for you guys on the calculator because you're just plugging in new numbers. Other two people, help them out as they do it. P.S. on homework, as long as they're equally spaced, you are okay just to go straight to this final line. You don't need to show me like the whole setup with A1, A2, A3. If you guys have 4 people in your group, please make sure the last person knows how to do it, even though they weren't forced to. I'm going to trust you guys on this one. It's a little too much math for me to do by hand right now. Anybody else get 18.25? Yeah, keep working. It's okay. Take your time. I'm going to go ahead and draw my rectangles while you guys are doing that. Because my question to you is, what do you guys think, over or under? Could you tell, using your calculator, whether it's an over or under? What could you do that we haven't actually done yet? Do the yellow, plug it in, and get the exact. You could actually use the integral button. So if there's a 4th person in your group, have them plug in the actual integral. If not, whoever wants. You can compare it to the actual integral. I'm going to draw a picture and we'll try to make sense of it. So we have our 0.5. 1.5. What's the actual integral from 0 to 3 of 9 minus x squared? Once again, me showing you a peek behind the curtain that we actually haven't done yet. Was it 18? Some of you are like, I'm not even paying attention because we haven't learned it yet. Some of you are like, I think she anti-derived and then plugged in stuff like she did. But anyway, how did this compare? Over or under? Over. But barely. So if the actual answer was 18.45, this one was an over approximate. But barely. Which one seemed to be more efficient? The left, the right, or the midpoint? The midpoint. But which one took kind of, if you were to do it by hand, which one would take more work? Ugh, those fractions, right? Which is why when we went back and did this whole like, hey, you can actually tell a computer or a calculator to do it for you, I didn't use the midpoint. I didn't try to hit halfway in between each of my subintervals because I'm like, whatever, I'm going to 10, 100, 1,000, a million. I don't care. I just need one of them. And to be honest, the right-hand one is the easiest because it says start here and then go out and hit. So if you notice, these rectangles that I did right-hand approximations because it's the easiest one to write down. When you try to summarize into some sort of concise, condensed, here you go, computer, solve it for me, please. But this one was going by tens. Hey, wait a minute. What if this was going by tens? What if this was going by tens? What if I was to have to do A1, A2, A3, all the way up to A10, and let's say we were doing from the right, and we were trying to approximate The same exact guy, which is the integral from 0 to 3 of 9 minus x squared dx. How could we have gotten even better approximation? Because with n equals 3, there was a lot of space in there. There was a lot of error. Because what would change? I'm not going to make you do it, but what would change if we had gone by 10s instead of by 1s? The approximation would have been better, but just real quickly, just to make sure that we have the idea of what's going on, what would my delta x have been? Not 10 minus 3. We still just have a distance of 3, right? But what are we cutting it into now? Ooh. So then we would have had to go from 0 to 3. What are we going by, 3/10? Pause. What is that as a decimal? Make it easier. 0.3s. So we'd have 0.3, and we'd have 0.6, and we'd have 0.9, and we'd have 1.2, and we'd have, But that's okay. What would have changed over here? F of, remember on the right, that guy, right? Times 1. Oh, nope, 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 nope. It wouldn't have been times 1 because that's not my base. What would my base have been? 3/10. So times 0.3. What would my next one have been? F of 0.6 times, what's still my base? 0.3. What would my next one have been? Times. Remember how I said you don't necessarily have to write out your A1, A2, because if there's an A10, like, it's so tedious. But approximate area, we're doing from the right. How would you put it in your calculator? Simplify math a little bit and not make you do all these computations. Come on, all done. At least we're seeing someone else. Pull out the 0.3. Save yourself a lot of time because they're all going to have it. And then what are you going to do in here? Y1 of, right? Y1 of, right? How do you know when to stop? When you get to 10 of them, good. Which is also going to land, have you guys noticed whenever it's on the right? Where are you going to end? You're going to end at 3. You're going to get everybody except the far left. Or when it's a left-hand approximation, you're going to get everybody but the 3. That's the way to double check. You're going to get it all the way up to f of 3. You're going to hit enter and be like, give it to me, please. Right? Make the computer, the calculator do the work. But how would this have been rewritten as a sum? To 10 of f of, let's see if it works. A plus, because A is the beginning, B minus A, all over N times K times B minus A all over 10. Wouldn't that be easier to plug into your calculator? Pause. Would it work? Plug in K is 1. 0 plus 1 3/10. Is that going to be f of 0.3 times 0.3? Plug in 2. 0 plus 2 3/10. Isn't that going to be f of 0.6 times 0.3? Plug in 3. Plug in 4. Now, guess what's really cool? What if we could do this? Guess what that would do? You were just sectioning into 3, then you were sectioning into 10, then if you section into, what's going to happen? If we can have the number of rectangles being squished into a finite space approach infinity, then we can solve the integral. That's the cool thing. Remember how we used to have to solve the the derivative using the definition using limits, and it was gross? In BC, we never actually have to fully understand how to do this by hand. In AB. We never have to actually figure out how to do this by hand. Why? What have you seen me doing a couple times now when it comes to this? Am I solving it with a limit and a summation? I'm solving it with a really seemingly simple subtraction with antiderivatives. In AB, you are never asked to actually do this by hand. What are you asked to do? Not the infinite, not the limit of a sum, because we don't really dig deep into summations and series in this class. That's more of a BC idea. I could show you how this works. Maybe I'll show you at some point this chapter before the next test. I could show you how this works, but we don't have to fully understand the limit definition of an integral. But you're going to play with, in homework tonight, getting ready for, finishing section 4.2, you're going to play with much smaller sums. N is 3, N is 5, N is 10. Plugging in, maybe with decimals, maybe with yucky fractions, but using your calculator to approximate from the left, from the right, and from the midpoint. Sound good? All right, bye guys. Homework due? Oh, hey, we already did that. Tomorrow. Good job, good job, good job. Those of you that don't take your calculator home, take it home tonight, or else it's going to be really sad.